Dr. Shamkant Anwane. I am professor and head of Department of Physics at Shri Shivaji Education Society, Amravati's Science College, Nagpur. Here we have purchased Geekin digital podium, and we are trying to record and stream the lecture for the first time using this system. And for this purpose, today I am going to talk about the derivation of Dirac's equation. The starting point of this equation, I would like to begin with wave equation. And in quantum mechanics, this is an advanced step, and it is expected that you are aware with the wave function. Wave function psi is function of position that can be represented by r bar, and it depends on time, and this can be expressed as some amplitude factor times e to the power minus I upon h cross. Inside bracket we have et minus p bar dot r bar. Here I would like to mention that E represents energy, T represents time, where you are evaluating the function. P represents momentum, space momentum, and r bar is position, where you are finding the wave function. Now, I want to develop operators, that is energy operator and momentum operator. For that, I am differentiating this wave function partially with respect to time, so that del t of psi, which is function of r and t, that is equal to a into to the power minus I upon h cross inside bracket t minus dot r bar. So e to the power function's derivative will be e to the power function times derivative of the function. So here it will be multiplied by the derivative of exponent with respect to time, and that will be minus I upon h cross into e. Derivative of t with respect to t will be unity. Now let us rearrange this equation so that we can make the things a bit compact. Partial derivative with respect to t operated on wave function psi is equal to the same wave function psi into minus I upon h cross into e. So minus I upon h cross into e times wave function psi. I further want to rearrange this equation so that h cross and I, they are taken on left hand side. So I am multiplying by minus h cross upon I on both sides. So partial derivative with respect to t operated on wave function psi, and here I am multiplying by minus I upon h cross. So I will be left with only e into t. Now further we can multiply denominator by I and numerator by I, and I square will be minus 1, so this will be cancelled. So finally we have what we call energy operator. I am going to denote energy operator E cap as I into h cross into partial derivative with respect to t. When we operate this energy operator on wave function, we will be able to obtain energy and the wave function. So if we employ this equation such that E cap, E hat operated on wave function psi will give you energy times psi. So you can replace this E cap by I h cross into partial derivative with respect to time. Similarly, we shall make a differentiation partially with respect to x. So del del x of wave function psi will be same wave function e to the power minus I upon h cross et minus p bar dot r bar into partial derivative with respect to x of this quantity minus I upon h cross multiplied by minus px into x plus minus I can take common py into y plus pz into z. So I'll simplify this so that partial derivative with respect to x operated on wave function psi will be this minus into minus will be plus. So I upon h cross into px psi. Now I further want to rearrange this so that I am multiplying by h cross upon I on both sides, or you can make a kind of adjustment h cross upon I partial derivative with respect to x operated on psi. This is equal to px into psi. Now I want to multiply numerator and denominator by I. So this I square will be minus 1. So we can write it like this. So I want to write a momentum operator as p cap, rather px cap as minus I h cross into partial derivative with respect to t. Similarly, if we differentiate with respect to y and z, we'll be able to obtain the momentum operator for y component and z component, so that the generalized p bar representation we can have px I cap plus py j cap plus pz k cap. If you like to differentiate again with respect to x, then you can obtain second order. I have made a mistake here, it should be x because this is x. Okay. Now I want to write p square. So px hat operated on px hat, this will lead to minus I h cross partial derivative with respect to x operated on minus I h cross partial derivative with respect to x. So this will try to simplify. So minus minus it will be plus, I into I will be I square, that is minus 1. So it will be minus h cross square partial derivative with respect to x of second order. Similarly, we can raise py hat square as minus h cross square partial derivative with respect to y of second order, and pz cap square will be minus h cross square partial derivative of second order with respect to z. And in toto, we can write p bar dot p bar as px square plus py square plus pz square. So we have to sum all three components, that will be minus h cross square inside bracket partial derivative of second order with respect to x plus partial derivative of second order with respect to y plus partial derivative of second order with respect to z. this can be fashionably written in terms of nebula operator as minus h cross square into this del square, not nebula operator, this is a Laplacian operator, del square. Now, we have raised energy operator, momentum operator, and we have raised momentum square operator. So P square will be minus h cross square into del square. Now, when we want to Schrodinger's equation, that is non-relativistic quantum mechanics I am talking about, there we are talking about energy as kinetic energy plus potential energy. So total energy E is equal to kinetic energy, which is 1 by 2 mv square, where m is mass of the object, v is the velocity of the object. So 1 by 2 mv square will govern the kinetic energy plus potential energy v, that will depend on position. Now this can be written as p square by 2m. So I am using p is equal to m into v. So p square by 2m plus v will be a better equation to look for the total energy of the system. And this I want to write in terms of operators and wave function. So this energy equation I am writing as E cap operated on wave function psi, that is equal to 1 upon 2m p cap square, that is momentum square operator operated on wave function psi, plus v operated on wave function psi. So this is what is called as Schrodinger's equation. So if you like to write energy operator in terms of time derivative, it will be time dependent equation, and this very equation we call time independent equation. Okay, so I want to replace E cap by IH cross first order time derivative, obviously partial time derivative. So IH cross into partial derivative with respect to t operated on wave function psi, this is equal to 1 upon 2m. Now p square I want to replace by minus h cross square upon into del square. So minus h cross square into this nebula operator operated on wave function psi plus v into psi. If a particle is free, this potential energy you can set to 0, and you can use this equation. It means Schrodinger has developed this equation, and this was used for various purposes that every student learns in undergraduate level. There we are using a particle in box, a free particle bound by infinite walls. Then there are many such applications, and it is used for hydrogen atom also, and hydrogen atom spectrum was successfully studied by Schrodinger using this equation. But later on, after the discovery of special theory of relativity, the energy equation was rewritten, and to go towards relativistic approach, I am going to write the new relativistic energy equation. So here we are going to use Albert Einstein's equation for energy, and that is a very famous equation for energy, which is called as the relativistic energy of the particle. This is wave function, basic wave function psi, with which we have started, and according to Einstein, E square is equal to p square c square plus m0 square c to the power 4. Now we want to employ this for quantum mechanics, and I am rewriting this as energy operator E cap square operated on wave function psi plus that is equal to p is minus h cross square del square multiplied by c square plus m0, this is to be operated over wave function psi plus m0 square c to the power 4 operated on wave function psi. Now here, if we replace E cap square, what should we do? We have to operate this operator again on itself. So it will be I into I, that is minus 1, and h cross square. So minus h cross square into second order time derivative operated on wave function psi, that is equal to minus h cross square c square operated on wave function psi plus m0 square c to the power 4 operated on wave function psi. This is known as Klein-Gordon equation. This is one of the forms of Klein-Gordon equation. Now, Dirac was not very much convinced by this equation because here we are having second order time derivative. And I am writing this del square operator here. So this is second order space derivative. So solving second order differential equation is troublesome in one sense, but however, if we go through complexities of that equation, the problem is that the solution is not confining to a convergent point. It is for a region, and that is not a good solution. So success of this equation for hydrogen atom was a step down as compared to Schrodinger's equation. So Dirac has used a wonderful idea, and objective of my lecture today is to tell you that idea which made him go up to the Nobel Prize in physics. Now what he did, he took square root of this equation. So E is equal to plus minus under root of p square plus m0 square c square. One c I am taking common, and when it comes out of the root, it will be simply c. Now, to avoid complexity of equation, I shall set a coordinate system in which c is equal to 1. We are preferring units where c is unity, and under that situation, our equation will be E equal to plus minus under root of p square plus m0 square. Now, this equation will be a first order differential equation, but there are some problems associated with this, and he tried to wrote that some factor, what he did, p square plus m0 square under root, he wrote as some parameter, say alpha times p plus another parameter beta times m0. Now, if you square this equation on both sides, what this will lead to, let us rewrite this equation. So this will lead to p square plus m0 square. We can replace alpha times p plus beta times m0 square. So we shall square. We are not knowing what alpha is and what beta is. So we have to treat them in a very respectful way, because we are not knowing whether those are numbers or some other objects. Now, when we find the square of such quantity, alpha p will be operated on alpha p, that will be first term. Then the last term will be beta m operated on beta m, and the mixed term will be like alpha p operated on beta m and beta m operated on alpha m. Sorry, alpha p. Now, if we employ this equation, what we can do, we can write this simply as alpha p plus beta m. Now, E is equal to alpha p plus beta m. This will be a linear equation of first order. However, we are encountering with this situation wherein what we expect, that alpha into alpha, which relates to alpha square. I am rewriting this equation: alpha square p square plus beta square m square plus alpha into beta plus beta into alpha times p into m. So p into m is equal to m into p, that we already know, but we are not aware with what alpha and beta is. So we have to honor the order of operation of alpha on beta and beta on alpha. So for this to be correct, so this should be equal to p square plus m0 square. For this to happen, we need that alpha should be 1, alpha square should be 1, then beta square should also be 1, and alpha into beta plus beta into alpha, this should vanish. If it is so, then this equation will be correct. So these are the restrictions on alpha and beta. Now, if you consider that alpha and beta are number, then 3 into 2 will be 6, and 2 into 3 will also be 6. So that will lead to number 12. So this is not permitted. So we gather basically information here that alpha and beta are not normal numbers. They are some objects which should behave in this fashion. So I told you this with a simple example, that we are encountering with p square and m square in a simple way. But actually, p is not that simple. It is a vector quantity. So p square should be px square plus py square plus pz square. And the multiplying factor also has to be of that kind, so that alpha also should have 3 components, like alpha x, alpha y, alpha z. And here this p into r we have to understand, and here alpha into p we have to understand. So alpha into p should be alpha x px plus alpha y py plus alpha z pz. So this is a bit complicated situation. We'll just try to unfold that, and I'll be able to very appropriately communicate to you what Dirac has done. So I would use this space for further derivation. So we have considered this alpha into p as alpha x px plus alpha y py plus alpha z pz. So our basic equation will be px square plus py square plus pz square. This I am writing for this p square, and then plus m0 square. This should be equal to alpha x px plus alpha y py plus alpha z pz plus beta m0. So we have to write this quantity like this, and we have to consider square of this. So instead of alpha and beta, we have four factors: alpha x, alpha y, alpha z, and beta. And when we are taking square of such quantity, we'll be talking about alpha x into alpha x, px into px plus alpha x into alpha y, px into py plus alpha x into alpha z, px into pz, and last element with this beta m0 plus alpha x into beta, px into m0. So this way you can raise 16 elements, wherein this will be alpha x square, this is alpha x alpha y, alpha x alpha z, alpha x beta. Similarly, the next will be alpha y alpha x. So py px plus alpha y py py plus alpha y alpha z py pz plus alpha y beta py m0. So in this fashion we'll be able to obtain alpha x square, alpha y square, then here this will be alpha z square, and then here this will be alpha z square will be below this alpha z square, and then beta square. So we want all these quantities to be unity. And last line. So I'll shortly write that alpha x square equal to alpha y square plus alpha z square, not plus, this is equal to alpha z square plus beta square. This should be unity, and all other mixed products should vanish, like alpha x alpha y should be 0. Similarly, alpha y alpha z should be 0. Similarly, alpha z beta should be, rather I should write the in between term first. Alpha x alpha y alpha z, and then alpha x alpha z. Alpha x alpha z, this should also vanish, and beta with all alphas, that is beta with alpha x should vanish. Similarly, beta with alpha y should vanish, and beta with alpha z should also vanish. So this is the requirement. Normal numbers are not showing up to this, but if you write alphas, I mean alpha x, alpha y, alpha z, and beta in terms of Pauli's matrix of fourth order, then these conditions are satisfied. And the most interesting thing is that these requirements intrinsically represent spin of the electron. That is the beauty. And one more thing is that here we have encountered with plus and minus sign. So plus sign indicates matter and minus sign indicates antimatter. So Dirac did this in 1928. He was very convinced by what he is doing, whereas the contemporary scientists did not appreciate his approach, but later on he was correct. His prediction of antimatter in 1928 was indigestible for his contemporary scientists, but his work was considered for Nobel Prize, and this subject of relativistic quantum mechanics has taken a way up which has probably changed the course of modern physics to a great extent. At this point, I would like to stop. Thank you very much for your attention, and subscribe this channel for such more lectures. Thank you.